I'm so excited about this talk that actually Steph gave a talk to my lab 6 weeks ago or so, and had lunch with everybody pretty much but me and Aaron, because I was home with sick kids and Aaron was in someplace else. So super excited to actually be able to sit down for one of Steph's seminars. Dr. Steph Brodie actually did her undergrad here, so when talking about things around UQ, I actually had to stop her so I could be like, wait, that's everything I do. She did her undergrad here, and then she went to UNSW for her PhD before going to California and working with some folks that I know from way back on her postdoc, which included a fair amount of work on dynamic management, which is also very close to my heart. So very excited to have Dr. Steph here today. And now she's come back over to Brisbane, and actually we ran into each other at tea several months back. So a plug for the benefit of coming to tea and meeting folks at tea. Steph's work currently at CSIRO is more around plastic debris and modeling plastic debris and the like. But today's talk is ecological forecast for resource management during climate extremes, more related to the, I think, your postdoctoral work in California. Yeah, so that just means that we'll be able to get Steph back again in the near future to talk about that plastic debris stuff. Okay.
Nice.
Thanks.
Okay, thanks for the introduction and thanks for having me along today. I'm excited to give this talk. So I've been at CSIRO for maybe about 5 months now. It's a new position, but today I kind of wanted to talk about a more established kind of project that I was working on with NOAA Fisheries and UC Santa Cruz, based in California. And this was really kind of trying to develop ecological forecasts for end users in the marine space to help them deal with climate change. Okay, so climate change is upon us, we all know that. Society is increasingly facing these novel and uncertain conditions, thinking about these extreme events, which we're all very familiar with. But these extreme events that are happening at the physical level are really cascading down to the ecosystem level and having unprecedented impacts. So this is from species changing their distribution across the entire ocean to negative wildlife interactions, particularly with fisheries, and also with ocean health underneath that little sign there, with fish kills and kind of cascading up to marine mammals as well. So really to kind of get a handle on what's happening in the ecosystems, we really need accurate predictions across all forecast horizons. So this is thinking about forecasting what's going to happen tomorrow, next week, next year, in 10 years, in 100 years. But decisions change across timescales depending on where you are. So thinking about decisions that might be made in the coming next 10 days, at least for fishing, you might be thinking about, is that showing? No, okay. Thinking about looking at a weather forecast for fishing in a particular region. As you move out, you might be thinking about when to hire labour, whether you should fix your boat, that kind of thing. As you move further in time, looking at year to 10 years, fisheries management and kind of harvest strategies come into play. And then when you're at this kind of decade or century timescale, it's really more about strategic long-term planning. And so seasonal forecasts are really kind of targeting this intermediate weeks to out to a decade or weeks to year for seasonal forecasting, moving out to the decade. And these are really rapidly needed to support adaptation to these climate extremes that are happening at those timescales. And so if we want to forecast ecology at any of those timescales, it really relies on ecology itself being predictable. Sounds easier than done. But ecological predictability can come from a number of sources. It can come from life history traits that are very predictable as animals grow and reproduce. It can come from persistence of the ocean. This is the idea that the ocean tomorrow is going to look a lot like the ocean today. It can come from animal phenology, so thinking about animal migrations, from passive advection as oceans move, particles around, and it can come from species distributions. And this is a lot of the work that I do, thinking about how animals like particular environmental features and they track those features in the ocean, and that's what their distributions are. So when you kind of move into this forecasting context, there's a number of ways that you can really harness that ecological predictability to create ecological forecasts. So your first option is to just simply use the physical environment. So this is one example of the east coast of the US, where they use temperature observations on the seafloor to predict when lobsters will begin their migration, and share that information with fisheries who can then kind of time their fisheries operations with that migration. You can also just simply use ecological observations. This is option B. So looking at autoregressive models predicting distribution shifts, using models to predict life history kind of traits as well. And then option C is where we can kind of couple both of those. We can integrate both ecological traits and physical forecast system to actually develop an ecological forecast. And this is perhaps been quite commonly used, especially in Australia. And one example is the timing of tuna migrations for tuna ranching off southern Australia. This is the idea where you have a physical forecast system coupled with an ecological model, a species distribution model. So this is a pretty kind of rapidly emerging field, and there's a number of examples that exist already. I'm just going to focus on a few NOAA-based ones or US-based ones, just rather than focusing on the Australian ones, as they may have already heard a few talks from the Australian space. But some examples of operational forecasts are Coral Reef Watch, which has already been a few talks this year on that here. There's forecasts looking at pathogens and when predicting when shellfish will become toxic for human consumption. There's lots of different forecast systems around the world of harmful algal blooms. And recently we've also developed a marine heatwave forecast. This is global, but creating or forecasting marine heatwaves out to 1 year in advance. At the more kind of ecological scale, so as we kind of move up from the physical to the actual ecosystem level, there's now cast to look at reducing fisheries bycatch and turtle bycatch, as well as forecasting salmon returns for stock management, and also forecasting when annual catch limits will be met. And that's another kind of fisheries management tool. So a little bit fisheries focused here. The next frontier when we kind of start thinking about ecological forecasting is shifting that forecast horizon out from a few weeks to a few months out to the next year to the next 10 years. There's only really a handful of published examples that have done this. So one example is actually forecasting big-eyed tuna catch 4 years in advance, and this is looking at life history traits and foraging success in the Pacific. There's also physical forecast systems that have predicted flow fillet and fisheries landings up to 3 years in advance, net primary productivity 3 years in advance, and I think perhaps the first demonstrated example of an ecological forecast predicting fish habitat 10 years in advance, which is a massive achievement. Okay, so what I wanted to focus on for the rest of the talk was thinking about continuing to develop ecological forecasts, and the idea that we already have a large number of management tools in the ocean that we use for conservation fisheries objectives. And so I wanted to test whether we can actually just harness those existing tools that we have, but configure them to a forecast and see if we can actually give some leading information about what the future might hold for the decisions that managers are making now. So to do this, I'm kind of focusing on the California region, which is an upwelling system, but it has had a lot of climate variability in the past, including some very large marine heat waves that have kind of had very catastrophic ecosystem impacts. So we first wanted to test 7 different management tools that are targeted at conservation implications in this region. And the first step that we did was we actually looked at the skill of the physical forecasts. So can we actually predict and forecast just sea surface temperature, for example, and what does that mean for these tools? So this is 7 different tools, this doesn't work, in this table here, all kind of focused around fish and marine mammals and sea turtles. And each of these management tools have different spatial, temporal kind of regime, well, not regimes, but bounds to them. And there's a different number of kind of physical variables that are used to set these decisions. And so by looking at just the skill of the physical forecast, which is this plot here of the anomaly correlated coefficients, you can kind of see that there's a few of these tools that perform really well and a few of these tools that don't perform as well. And so it gives us just this very quick indication of which tools might actually be informative at an ecological forecasting scale. And so this is where we landed on two tools to actually test our approach. One is called Total. It's a tool designed to mitigate loggerhead bycatch in a drift gillnet fishery, and the habitat compression index, which is essentially a whale entanglement forecast. So I'm going to jump into these two examples to kind of get into the nitty-gritty of it. So the first case study is the whale entanglement tool. So in this region, we have dramatic kind of environmental change into annual and from climate change as well. So for example, marine heat waves will move into the area. They'll push these humpback whales and other whales in towards the coast, where they overlap with a very lucrative crab fishery, which then leads to fishery closures. So these fishery closures are really great at mitigating whale entanglements. Basically, there's no one fishing, so you don't get entanglements. But they come at a very, very large socioeconomic cost for the state. So to kind of get a better understanding of why this was happening, this management tool was created called the Habitat Compression Index. And this is just an index of how much upwelled water, or where upwelled water is in the California current. So in this region, the whales forage in this nutrient-rich upwelled water where all their prey is. And so in an example year, this is 2013, this is a map of sea surface temperature, and you can see this cool blue water is where the upwelled water is. In 2016, we had a marine heat wave that came in and pushed this kind of like hot, warm water in. And so this narrow strip of upwelled water is kind of compressed along the coast, and this is where you get that whale compression right up against the coast. So if you measure the amount of area that upwelled water is taking up relative to the historical kind of observed data set, it decomposes into this really nice time series. And so everything kind of shaded in red is when we have these high habitat compression events that essentially equal like high risk for whale entanglement. So now that we have this time series of a fancy sea surface temperature index, we thought, well, why not just use forecast sea surface temperature and see if we can actually forecast this habitat compression up to a year in advance. And so that's what we did. So we used these global sea surface temperature forecasts from the North American Multi-Model Ensemble, the NME. There's 6 global models. Each of them have their own number of ensemble members, but we basically had 73 sea surface temperature forecasts that we worked with. And this is an example of what that looks like. So the black line here is the observed habitat compression index. And it's the exact same time series as before, but we just zoomed into a particular time, 2013 to 2017, where we had this huge marine heat wave that came through. And as that black line drops below the horizontal threshold, this is where we had huge habitat compression. We had a number of whale entanglement events. And this was kind of a very risky time for whales in the California current. The coloured lines here are what our actual forecasts were for that time period. And it was a forecast 1, 7, and 12 months into the future. And so you can see that all these coloured lines kind of follow the exact same trend. And so what we're showing is that 1 month in advance of this kind of these whale entanglements happening, 1 year in advance, we actually could have forecast those risky conditions, and that could have had implications for how we managed that fishery instead of having so many whale entanglements that we actually had. Okay, so Because we have the benefit of looking back in the past with all these models, we conducted a retrospective forecast. So this is where we actually created a forecast for every single month from 1981 to 2020. So for every month of the year, which is the x-axis here, for every lead time, which is 1 to 12 months that we're generating forecasts, we created a forecast and then we actually compared it with what was observed at that exact time. And so by doing a correlation between forecast and observed, we could kind of test whether we were any good at it and whether we were any good at it over this kind of historical period. And so everything is in red is showing that we had a positive correlation. Everything in with a black dot is statistically significant. So what we found is that during winter and spring, we actually had the ability to predict these compression events 12 months into the future. That skill then kind of degrades as we move through into summer. But this time period of winter and in spring is actually the perfect time. That's when they actually really want to know when these risky conditions are happening and when they want to implement some of their management strategies. So some of these kind of potential management actions that can happen during these high risk conditions are actually putting out fleet advisories. So telling all the fishermen that this is a risky time, that there are lots of whales around. There's also fishing depth constraints, vertical line reductions, actual just complete closures of certain zones. These are just particular management zones, and using alternative gear for this fishery. And so these kind of fleet advisories and fishery closures are two of the management actions that actually could be informed by this forecast. So we could say to the fishery and the relevant stakeholders that, okay, 1 to 12 months from now, we're expecting a potential kind of high risk event. Okay, so the second case study that we thought we'd have quite good skill at was this Loggerheads sea turtle bycatch management tool. So again, off the coast of California, we're kind of zooming in to work on the California bight here. Loggerhead sea turtles like to hang out of Baja, California, Mexico. But when marine heat waves or El Nino conditions happen, the water's warm off the Southern California bight. These loggerheads actually extend their habitat and their distribution further north, where they overlap with a swordfish-driven fishery. So the typical management response is to actually close this fishery during those conditions, those hot conditions. And the way that we kind of test whether things are hot is by using sea surface temperature anomalies in this square box in the Southern California bight. And so when sea surface temperature anomalies exceed this red line, we have a fisheries closure event. So it's the same logic that we're using observed sea surface temperature anomalies. So why not try and use forecast sea surface temperature anomalies and actually give some lead time as to what the ecosystem conditions are going to be over the coming year. So we did the same thing as I kind of showed for the whales. This is zooming in on that exact same marine heat wave that happened in 2014 to 2016. The black line is our observed sea surface temperature anomalies. And in this case, when things go above the line is when we have a fisheries closure. And so when things are above those horizontal lines, it's a fishery I'm just repeating myself, it's fishery closure. And these coloured lines are our forecasts, and you can see they're following the exact same trend. And these are forecasts 7, 9, and 12 months into the future. So again, we've got, up to 1 month, 1 year in advance warning of these potential fishery closures and these kind of potential loggerheads increasing their distribution in that particular region. And for the retrospective forecast, and looking at the correlations between observed and forecast conditions, again, we're seeing very good correlations, and we actually have statistically significant skill in all of the closure months. There's only 3 months a year that there's potential closure in the management action. Okay, so before I go to the next slide, that was using global sea surface temperature forecasts, kind of demonstrating that we can do this, we can change these management tools not change them, but provide a forecast information 1 year in advance, kind of transfer them to this forecasting configuration. But we also have a downscaled forecast for the region that we had to play with, and we're kind of lucky enough to have this. So the global sea surface temperature forecast that I've already been working with, we had 73 ensemble members from 6 global models, but it was a very coarse resolution. It's 1 degree. It's only once per month that we can get that information. We, in a kind of separate study, we actually regionally downscaled these global forecasts to the California current, to a bronze model, where we have much improved spatial resolution of roughly about 10 kilometers, and they're produced every single day. But the kind of trade-off here is that we don't have enough computational power or enough storage to actually kind of run this for 73 ensemble members. So we chose 3 ensemble members and downscaled those 3, which is pretty common when we come to downscaling. So we wanted to test what the effect of this was on our forecast, because creating an operational forecast at downscale sea surface temperatures is a lot more challenging than just using the global ones that are readily available. So I wanted to kind of ask, do we need to downscale, and what's the benefit? So for the habitat compression index, this is the same kind of plot I showed before of all the correlation values between observed and forecasts, and now just in a pretty box plot. And this is for our 73 ensemble member model. If we just use that exact global coarse scale resolution, but only pick those 3 models, then we get a decrease in skill. And this is kind of expected as you only select a handful of ensemble members, that you will get that decrease in skill. The question is, now that we have these 3 ensemble members, what's going to happen with our downscale results? Are they going to get better? Are they going to get worse? What's the benefit of downscaling here? And what we see is that it does improve. So downscaling does improve your forecasts, but only having 3 ensemble members isn't enough to actually improve the forecast to greater than what you get from global models. So having these kind of 73 ensemble members is actually giving you better skill in this region, because it's better characterizing the environmental variability than just kind of zooming into this downscale resolution. So there's lots of kind of pros and cons to downscaling, staying at the global level. I won't go through all of this now, but there's lots of kind of decisions to be made by the practitioner. Should you downscale, should you not? What's the added benefit? Some of the for downscaling to, I guess some of the benefits to downscaling is that you can get certain variables that you can't get out of the global models. So thinking things like biogeochemical variables. You can get improved spatial and temporal resolution. But sticking at the global forecast level means that you have operational, readily available forecasts to use right now. There's kind of nothing stopping anyone to actually start creating ecological forecasts. Downscape, there's kind of this additional like accessibility component here of, knowledge and expertise is that to work with downscale or to do downscaling, it's quite challenging. And I think that's quite a barrier to this kind of continued uptake of the ecological forecasts. And then finally, the accessibility of the global forecasts, which I've kind of already mentioned, is a huge asset. That they're open access and ready to go. So with that, I guess I'll kind of wrap up. And the quick kind of takeaway and take-home points are that we have capacity for existing management tools to transition to a forecast configuration. That ecological forecast can forewarn of these human-wildlife interactions. And the final point is to kind of encourage you to not wait for regional downscaling. If you are waiting, you can kind of charge ahead already with these open access global sea surface temperature forecasts. I'd also like to thank all co-authors that contributed to that work. And that's kind of the wrap up of the California component of, I just kind of wanted to give a case study as to some of the things that I do. But now that I'm at CSIRO, I am kind of working on a number of different aspects. And so my research program really looks at biogeography, so looking at the different biotic and abiotic factors that drive species distributions. I'm working in climate variability and change, looking at climate impacts on living marine resources and their dependent communities, and kind of with the lens of those I often work with fisheries case studies because I find them fascinating. And so looking at specifically a lot of bycatch and management solutions to this kind of issue of climate change. And I'm also working in the marine debris space. So looking at understanding sources, sinks, and then impacts of marine debris on our ocean ecosystems. And that's it. Thanks for listening.
Good stuff. Questions?
Thanks, Steph. That was really cool. I guess it's kind of an obvious question, but like the recent years in those plots seem to be like there's a threat of habitat compression all the time, and obviously the ocean's getting warmer. So do you have a vibe of like what's the policy plan there? If it's like every year now we're going to be looking at seasonal closures, or do they have a plan? Do you have a suggestion?
It's such a great point. It's one I've been grappling with lately, of this kind of shifting baseline that our ecosystems have warmed so much already that kind of comparing things to an old climatology that doesn't change isn't going to tell us about anomalous events anymore. And we really need to start kind of shifting that historical climatology so that we actually can pick those out. But that's not to say that we should exclude the first instance. I think we kind of need both, because it's important to detect and communicate what an anomaly is relative to kind of recent conditions. But it's also, you know, animals don't respond to anomalies, right? They respond to absolute conditions. So you can't kind of say to an animal like, oh, like, you know, this isn't that hot, when they're actually kind of being boiled alive. So it's a tough one, and it's one I'm still grappling with in terms of kind of communicating to stakeholders and audiences, because there's two issues here, and both need to be communicated, but it gets into the nitty-gritty pretty quickly. So for this exact example, I'm not sure what their plan is, but yeah, one we should flag. Good question.
Yeah.
Hi, so thank you for your talk. Have you incorporated like time thresholds into any of these like marine heat wave forecasts to consider? Okay, the heat wave really goes for like a couple of weeks compared to 3 to 4 or 5 months. Are you able to incorporate that into the type of management strategies that you suggest?
Yeah, it's a good question, and I think there's definitely a lot of scope to do that. And what we're seeing in the marine heat wave literature so far is like every marine heat wave is different. There's no like consistent impact or consistent story on the ecosystem level. So lots of scope. I guess one of the benefits to kind of asking this question of like, can we just use an existing tool and forecast it out, means that we have certain bounds on what we are forecasting, because it's a tool that's already being used by management. It's been accepted by various kind of wider fishery stakeholder community. So you don't have to develop a whole new tool and then try and get that taken up. So yeah, I guess it's two sides of the coin in a sense. But yeah, lots of scope to kind of continue.
So obviously for those examples, sea surface temperature is really important, or the anomalies. Are there other oceanographic processes or variables that are, I guess, maybe mitigating some of what's going on, or were they less important?
No, I think there's so many variables going into it, that complicated of where species move, and it's, you know, we do a lot of modelling, like species distribution modelling, for example, where we might have 10 different variables that are best explaining an animal's distribution, but we can't forecast those 10 variables because we're just not there yet. They're either not provided or there's just no skill in them. And so that's where you kind of have to start simplifying your models if you want to start forecasting. But with that, you then start losing some of your signal and your ability to actually detect what's going on. So there's no perfect solution, sadly. Yes, and you know, in the California currently, saying sea surface temperature as the only indicator of upwelling is incorrect.
Yeah.
But it works really well for these kind of habitat compression, but it's more nuanced and complicated.
I was going to ask whether, like, what constitutes these fisheries closures, and do these forecasts really prompt a fisheries closure, or do the fisheries perhaps weigh up the costs of entanglements and conflict to closure?
Yes. So for the whale example specifically, the group that decides on a closure is, I guess, an interdisciplinary, varied stakeholder group. So there's fisheries representatives, there's state, people from the actual fishery sitting on the group. Then there's a state fisheries representative, federal fisheries representatives. There's independent researchers that sit on it. It's quite broad, and they meet every month and discuss what's going on in the ecosystem currently, and what has been observed. So they're kind of thinking, at the moment, the information that they have is either present day or historical. But next month we're kind of starting to kind of introduce this tool and start thinking about, okay, well, what if you start having this forward-looking information? Is that going to change your decisions at all? And will you take a more precautionary approach or not? So there's, this would just be one tool in the toolbox that helps, hopefully helps make their decisions. Another example is that they have planes doing whale surveys, and if there's an observed whale density that exceeds a certain threshold, then that zone is closed. And so they've got these very specific rules in place that they kind of now can say, like, okay, if this criteria is met, then this area is closed. But I think having this forward-looking information will give everyone a little bit more of an idea of what might be coming down the pipeline, so to speak.
Yeah, because often we have a bit of an approach where you only close it after the entanglements, or like after there's been a conflict, reactive, rather than preventative.
That's why this group has been pulled together, because in 2015 the number of entanglements skyrocketed, and it was a huge concern, and that implemented a fishery closure. They created this group, and now there's this group kind of trying to be more proactive about it. But if there is an entanglement, it's an immediate closure. Yes,
Thank you.
Yeah, good. Great talk, very succinct. You covered a lot really well. I bet you I missed this at the beginning of your talk. Sorry. But I'm going to ask a very simple question. When is forecasting is a subset of modelling? Right? When is something a forecast and not a model? I mean, are we using the word forecasting? Is there a definition of exactly when you can call a model a forecast? Because we've been modelling fish population dynamics since 1920. And is that a word? And is the word forecast a great idea, because people use the weather forecasts, which are vaguely reliable after a few days. But generally, we're very suspicious of models because of the baggage of so many models, economic models, or even models not being very accurate. Do you want to talk about the semantics of the words?
Sure. Look, I'm sure there's somewhere that there are very specific definitions that I'm not going to be able to actually probably repeat them verbatim. But I think all predictions and forecasts will come from models. So it's kind of like the next tier down. So a forecast is a model, but a model is not necessarily a forecast, as you just kind of alluded to. But you then can have a model that makes a prediction, but that prediction is not always a forecast. So I would say that a forecast is making a purposeful prediction about the future based on an input of, I guess that known future. That's a good one. I'm gonna think about that more.
I googled it. And everybody in Google world is also confused.
Yeah.
But I mean, I think it's a master stroke, calling it forecasting. I'm just wondering when I'm allowed to call something, I could just rewrite all our papers and call them forecasting. I think people will believe us a lot more.
I'd say if you're calling something a forecast, you should validate it. You should validate it against,
Forecasting stuff.
either a retrospective forecast to really kind of test whether those.
So a lot of our models have been forecasts. In the last 20 or 30 years, people did those things,
Right.
but we just didn't call it forecasting.
Do you call it a model predictions?
Exactly.
Yeah. Yeah, I think like forecasts are predictions, but when the prediction is not a forecast, I'm sure there's a very specific cutoff point and definition there that I'm not thinking of on my feet right now.
Oh, just a really quick question, sorry if I missed it, so you've got this expert body or committee with stakeholders on that makes a decision about the closures. Is that under state fisheries legislation or wildlife legislation, or is it a federal thing, or is it a mixture?
It's a mixture. So the fishery itself is a state fishery, but because they interact with marine mammals, it becomes a federal issue because marine mammals are federally protected and come under the federal jurisdiction. So that's how the feds get involved. Yeah.
Thank you for a great talk, and you are a fantastic communicator. That question, so you really highlight the points about human wildlife coexistence. So do you think this kind of prediction or forecast can be used for the terrestrial animals? For example, Asian elephants. So based on some history, the very not in Euro long distance dispersal, all associated with extreme drought. So do you think, and this caused a lot of trouble because they left the forest, they need to go long distance. Like in China, they traveled 600 kilometers to the city to even different climate zone.
Right.
So do you think like any research looking into using this kind of global climate data to kind of using other terrestrial and animal cases?
Yes. Yeah, I think definitely a lot of potential there to develop a forecasting system. There's like kind of lots of options that are running through my head now of how to do that. So one example that's actually coming to mind is one that came out of Kenya, which tries to, well, that does predict forage condition for cows. And I'm probably not using the right terrestrial terms, but it uses, it couples a model that integrates kind of weather and climate data with a model that predicts green growth, and then does that spatially and kind of says where is good or bad foraging conditions for cows, and that's kind of meant to help the farmers and also help prevent famine in that region if there's drought. So they do that spatially in Kenya, and I'm happy to share that paper. But there's also lots of kind of other terrestrial examples that I'm kind of thinking of, but a lot of them are population forecasts. So kind of trying to estimate population size, not necessarily a change in distribution of an animal that, you know, causes conflict. But I imagine there's lots of potential there. Thank you.
Any other questions? I have one hard one for you at the end. The question I always ask Elliot and Rebecca Lewis, and they have no good answer for this. Why do we need a drift gillnet fishery, experimental drift gillnet fishery?
That's a good
Period.
question.
Right,
Okay.
so one of this it only applies to one of the two case studies, but one of them is for, maybe you can explain what a fishery is and why it exists.
Yes. Okay, so off the coast of the west coast of the US, there is a very rich pelagic ecosystem that draws in species from across the entire Pacific, sea turtles, whales, fish, sharks. In that region, there's a number of fisheries that, you know, fish there to provide protein and resources for its communities along the coast. Longline fishing is banned in the US West Coast EEZ because of bycatch concerns. Historically, okay, this is so much. Historically, there's been a drift gill net fishery because a longline fleet has been banned. So a drift gill net is just a large net that gets put out in the ocean and it catches everything. It's not discriminative at all. And so there's been a lot of bycatch concerns with that because it's just a net floating in the ocean. But there's been huge efforts to decrease a lot of the species of bycatch concerns, and it's slowly being phased out to the point where there's only a handful of boats now fishing. So swordfish itself is an important resource, fisheries resource protein for communities. So the question is, do you want swordfish out of your own backyard, knowing exactly what the bycatch concerns are and having observers on every boat or most boats, knowing what's going on in your backyard? Or do you import swordfish from another country where you have no idea what's going on, from a drift gill net out of, for example, Peru? Not, you know, that's just one example. There's many, you know, many drift gill net fisheries. So I'm not sure if that answers your question, probably alludes to which side that I'm on. But yeah, like it's something that I, you know, this.
I guess the question is sort of slightly broader as well, which is sort of at what point do we look at the fishery itself and we look at the amount of money that we're putting into the management of the fishery, and the development of forecasts and things like that to support the 6 boats that are catching these things, and decide that and this is not just in this case, like in many cases, right, fishery management is so much more expensive than actually what you're getting out of the fishery that it makes no sense whatsoever.
It doesn't when you think about it like that, of just monetary value, like money in, money out.
Yeah.
But you also have to think about the social value, right? The cultural value of having fisheries in your communities, fisheries in your backyard. And those social values will differ, you know, for various people. You know, some people will just be like, absolutely, I don't want a single boat in my waters. And others will want to support that local community and what that brings, not in just land use value at the dock, you know.
And
So-
someone always brings up the Hawaiian online case as well. These when they shut that down, then you had all these foreign fisheries come in and more turtles were caught. Yeah. I don't know if you hear that one. I hear that one a lot.
Yeah, right.
Yeah.
Yeah. I've got lots of thoughts on that. Longline fishing. Maybe we don't go there. But it is an interesting question because you do see it in a lot of Western nations, like a lot of money being poured into management and decreasing revenues from those exact those same fisheries. So where do you draw the line? And no, it's an oversimplification, but it's you also have to feed the world.
Yeah.
You know, we want to have a functioning ecosystem too. So how do you manage that? Yeah.
Okay, I think on that note, it's a good opportunity to stop and go feed ourselves for lunch, but thank you, Steph.